Correlation analysis is a statistical technique employed to quantify the degree and direction of linear association between two continuous variables. It serves to identify patterns of covariation, providing valuable insights into the interrelationships between variables. However, it is imperative to emphasize that correlation does not establish causality. 1. Conceptual framework of correlation. Definition. Correlation measures the extent to which two variables change concurrently. It assesses the strength and direction of a linear relationship. Distinction from causation. Correlation signifies an association, not a causal link. Confounding variables may influence observed correlations. 2. Typology of correlation. 2.1. Directional correlation. Positive correlation. Variables exhibit a direct relationship. As one variable increases, the other also increases. Example: a positive correlation exists between study hours and examination scores. Negative correlation. Variables display an inverse relationship. As one variable increases, the other decreases. Example: a negative correlation is observed between product price and demand. Zero correlation. No linear relationship exists between the variables. Changes in one variable are not associated with changes in the other. 2.2. Magnitude of correlation. Perfect correlation. The correlation coefficient is either +1 perfect positive or 1 perfect negative. Strong correlation. The coefficient approaches +1 or -1, indicating a close linear relationship. Moderate correlation. The coefficient falls within an intermediate range, suggesting a moderate linear association. Weak correlation. The coefficient approaches 0, indicating a weak linear relationship. Zero correlation. The coefficient is 0, signifying no linear relationship. 2.3. Linearity of correlation. Linear correlation. The relationship between variables can be accurately represented by a straight line. Nonlinear correlation. The relationship is curvilinear or otherwise nonlinear. 3. Carl Pearson's coefficient of correlation, R. Definition. Carl Pearson's coefficient, R, is a parametric measure of linear correlation between two continuous variables. Range. The coefficient ranges from -1 to +1. Interpretation. R equals +1. Perfect positive linear correlation. R equals -1. Perfect negative linear correlation. R equals 0. No linear correlation. The magnitude of R indicates the strength of the linear relationship. Mathematical formulation. Covariance method. R equals cov of x, y, the coefficient linear correlation, by sigma x asterisk sigma y, where cov of x, y equals 1 by n. Sigma x minus y, covariance of x and y. Sigma x equals standard deviation of x. Sigma y equals standard deviation of y. Direct computation method. R equals sigma xy, sigma xy, sigma xy, slash square root n. Sigma xy, sigma xy, squared. Sigma xy, sigma xy, sigma xy, comma y. Assumptions. Linearity. The variables exhibit a linear relationship. Normality. The variables are approximately normally distributed. Homoscedasticity. The variance of errors is constant across values of the independent variable. Continuous data. The variables are measured on a continuous scale. 4. Procedural steps for calculation. Calculate the means of the variables x bar and xi. Compute the deviations of each observation from the respective means. Calculate the product of the deviations for each observation. Sum the products of the deviations. Calculate the standard deviations of the variables. Substitute the calculated values into the formula. 5. Interpretation of results. The coefficient R provides a quantitative measure of the strength and direction of the linear relationship. Statistical significance testing can be conducted to determine whether the observed correlation is statistically significant. 6. Limitations. Sensitivity to outliers. Assumption of linearity. Correlation does not imply causation. 7. Conclusion. Carl Pearson's coefficient of correlation is a fundamental tool in statistical analysis, providing a quantitative measure of linear association. However, its interpretation requires careful consideration of its assumptions and limitations. It is essential to avoid inferring causality from correlation.